Hey everybody, welcome. This is Tom. I'm going to do a couple problems here, just a couple mechanics problems. These are out of the book, and this is on page 161, and it's question number 2. If you're watching this video and you don't know what book I'm talking about, it doesn't really matter. You can still watch these examples. Alright, so in question 2, it's broken into 4 parts, and in these parts, we are all talking about the same thing. It's going to be a floor here. Let me get that nice and straight as I can. Okay, and on this floor there is a box, or they call it a case. Okay, and we're trying to find the work that it's going to take to move this case in these different scenarios. And in this first scenario here, this case is going to move. I'll use a different color here. It's going to move 5 meters. Alright? And the case itself weighs 35 kilograms. And there is a force that's a resistive force, a resistance force here, that's going to be in this direction, and it's going to be 200 newtons. So this box is going to move from here, and it's actually going to move to the other side here. And the box, when it moves, it starts at 0 meters per second, a velocity of 0, and it ends at a velocity of 0. Okay, so it's starting and stopping at rest. That's it. Now, if we want to find the work that we're going to be doing, we're going to use the work formulas we've learned, and we've learned a couple different ways to measure, well, joules in this case. First is using this formula: work is equal to the force times the distance, or you might see it as work equals force times the distance, written that way. Right? And this problem here, this part 1 of this problem, let me go ahead and write here, part 1. They write it here like a little I. This is pretty straightforward. We have a force. We have a force here going in the opposite direction. We have a force this way. In order to get it moving, it has to be equal to this force, 200 newtons. Why does it have to be equal? Well, if you remember back to friction, you remember that in order to get an object sliding, the force has to be equal to the friction coefficient times the resistance, okay? Or times the resistive force. So in this case, this force going this way has to be 200 newtons as well. So we now know the forward force is 200 newtons because it has to counteract this backward force here. Could be friction, could be anything. All we know is it's some type of resistance. And so it's going to get pushed over here. So in order to solve this, we just do work is equal to 200 times the distance of 5, which gives us 1,000 joules. Okay. And that is the answer to question 1. Alright, now question 2, I'm going to scroll down here. Question 2 actually is the same setup, so I'll end up just, let me get a nice straight line here, same setup, but it's going to be a little bit different. So we have the box again, and this time we have the box. The box is still 35 kilograms, but when the box finishes over here, this starts at that there. This starts at 0 meters per second, or a velocity of 0. But when it ends, it actually has a velocity of 2 meters per second. So the ending velocity, there's still some energy in this box as it's going over here. Now, let me put the other values in here. We still know in this case that we have a forward force of 200 newtons, and we're going to have to use this information in order to solve it. We still have 5 meters here. Okay, so this case, it's really not too much different from this one to this one. For example, the box is still going to move 5 meters, and it still starts at 0, and it still has a forward force of 200 newtons, and it's still going to take 1,000 joules to get the box to here. So this still takes 1,000 joules in order to get the box there. But when the box gets there, when the box reaches this 5 meters point, it still has some extra energy. The box has what we have talked about as kinetic energy. So the box still has some kinetic energy. If you remember, kinetic energy is 1/2 mass times velocity squared. So in this case, we're going to take this energy here. It took us, this work here, same difference here. This 1,000 joules worth of work took us to get here, but we've added extra work into the box. We've increased the speed to 2 meters per second, and we're going to keep it going. So this here has kinetic energy, and if we calculate the kinetic energy of the box at this point, what we get is 1/2. The mass is still 35, and the velocity is 2 squared. And if you go ahead and do this calculation, what you're going to get is you're going to get 70 joules. Okay, so I have 1,000 joules and 70 joules, and if I put those two together, that is the amount I have at this point, at this exact point of 5 meters, right? When it reaches 5 meters, it has done, 1,070 joules worth of work. Okay, so that's the answer to question 2 is 1,070. Now, the next question is very similar. The main difference is, and yeah, I'm going to draw this one more time. And, it's all right. We know these by now. So we've got this and this. The only real difference here is that instead of the case or the box starting at 0, it actually starts this time at 2 meters per second, and this time it ends at 0 meters per second. Alright, so in this case it has an initial velocity, so that means when the box starts this 5 meters, it already has some energy. And by the time it gets done, it's lost that energy. So if we're going 2 meters per second, we already know that if we're going 2 meters per second with a 35 kilogram box, that we have a kinetic energy of 70 joules. So right now, our initial kinetic energy is 70 joules. Okay? And we also know that from here to here takes 1,000 joules in order to move the box from here to here if the box was stopped or the box has stopped and then gone up to 2. So it's going to take 1,000 joules to move. But we actually have this kinetic energy here that's coming in at the very beginning. So if it originally takes 1,000 joules, but we've started with 70 joules, that means the amount of work that is being done is actually 1,000 joules minus 70 joules, which is going to give us 930 joules. Okay? So in each of these cases, we have something a little bit different. This case up here, the box starts at a velocity of 0 and ends at a velocity of 0. And so it takes 1,000 joules in order to move the box from here to here, just using this simple formula we learned in class. Now, the second example here, we have the box starting at 0 and ending with some kinetic energy. So that means we had to calculate the work, 1,000 joules, and then add on our kinetic energy, the work being done there, which is 70 joules. So we end up with 1,070 joules total. And the last one, it's a little different. It's like kind of the opposite of this other one. And we have energy coming in instead of going out, and that means we subtract that energy from the total amount it would have taken us to get there. All right. Now, the very last thing here, this very last question, this number 4, is actually pretty easy. All it is the guy just standing here. Here he is. Yay, he's quite happy. Okay. And in his hands, he's been given this box. So, there we go. Let's fill this here. Alright, so he's got this box, and this box is still 35 kilograms. And he hands that box, and then his friend comes over. His friend happens to be blue in this case. Here comes his friend. And his friend takes the box from him and walks away. Okay, so in that case, how much work has this guy really done here? Well, if he holds it for 20 seconds, as in the problem said he's going to hold it for 20 seconds, and this guy takes it from him, well, his arms might hurt. It could be a heavy box. 35 kilos is not light. His arms probably hurt a little bit, so obviously he's done work, right? Well, actually not, because up here we know that work is equal to force times distance. Now, he might be working against the gravitational force, but the box isn't moving anywhere. So that would make the amount of work done 0. So in this last question, he has done 0 joules worth of work. Okay, and that might not seem intuitive, but that's just the way it is. We'll talk about it more in class, I'm sure. All right, so that is problem number 2 on page 161. And in the next video, I'm going to do problem number 4.